So you've mastered adding HOH, water, HOR, or ROH, alcohol, across the pi bond, have you? That's good, because the concept behind adding HX is exactly the same. We just replace OR or OH with X, and actually it's a shorter mechanism. You'll like it for that reason. So let's do the mechanism to tell us what the product is. So it's an acid, right? HBr. So just as we've been doing, and look, we don't have to do any equilibrium. We just know that the acid's ready to go. So what does the pi bond do? Does what it's always been doing and takes that H, the proton, and the electrons therefore stay behind on the bromide. We get our carbocation. Who's a better carbocation? Actually, you know what I want you to do right now? So we actually have to make that choice. Make one of those lines that looks like a methyl there an H. That way we have some selectivity. We could follow Markovnikov's rule, right? So when I draw this out, our framework looks like that with the pi bond missing. So we can evaluate, what do we rather with carbocation, there or there? Here it would be secondary. Here it would be tertiary. Definitely want that. Which means the new H goes on the other carbon. Tertiary carbocation. No opportunities to rearrange, because there's no resonance, there's no rings, right? So we're going to just be thankful we got tertiary and proceed with the next fate, which is to capture the nucleophile. Okay, so who's our nucleophile? We've been using water or alcohol in the past, which is not an acid, or at least not a strong one, but HBr is a little strong to be a nucleophile. But look what we just made in the first step. We made bromide. That's a great nucleophile. So that could come back to help us. Attack, it does. And I'll put this arrow up here so that it can circle back. Set this down right here. All right, so look at what we have here. We have Br and H added across the pi bond. We added HBr. So one part of it, the H went to one carbon, the one that already had more H's, and one went to the other carbon. The bromine went to the other carbon, the one that had less H's, the less substituted. So we could say it followed Markovnikov's rule, right? So we always summarize our new reactions right here. Regio selectivity. And we ask about stereo selectivity. Did it preferentially form one stereoisomer over another? Regioselectively, yes. The bromine, the X of HX, right? Because HX is the halogens. So we did this, a specific example has bromine, but we could do this also with chlorine commonly. Those are the two most common, chlorine and bromine, as usual. But just be aware that when we add them, the halogen is going to go to the more substituted carbon because that's where the carbocation was, therefore that's what the nucleophile attacks. So we're going to say it has Markovnikov selectivity. Stereoselectivity. Because we formed a carbocation, that bromine could have been a dash or a wedge. So no, it's not selective for one enantiomer over another. However, did we even form an enantiomer? If this was a homework problem and that your solutions manual or answer key had this written out in its most simplest form, it would look like this. The methyl would probably not be drawn in. There we go. It would just look like that. These are the same thing. The H's aren't always drawn in for you, right? We're drawing them in right now because they're new H's that we've just added, so it's nice to track them, but when you clean it up, it looks like this, and this happens to not have a stereocenter because it has two ethyls attached to the same carbon. But regardless, even if it did generate a stereocenter, no selectivity. We just have a racemic mixture, right? Now, there is a way to do the opposite. What's that, you say? There's a special cocktail for now. Unfortunately, it's going to be memorization because you're not really ready for this mechanism yet. But it's presented a little early in the book, earlier than when I cover it. So I'm going to let you have access to it as a tool. But if you see ROOR over the arrow, peroxide, the oxygen-oxygen bond, it can be a peroxide in the form of or HOOH, right? That's hydrogen peroxide, which is also written H2O2, which is also written R2O, like MEOOME. Lots of R groups could be, but the key to the peroxide functional group is the two oxygens. When you have that mixed with your HX acid, we can control it to get the opposite regioselectivity. Look at that. It went to the other carbon, not the carbon that was more substituted. So, regioselectivity. We would describe this regioselectivity as, and where is he? Right there. Anti-Markovnikov. The new group, the nucleophile, went to where it was less substituted. Actually, I'll put it here, just so we can kind of keep that in mind. You don't have to have that picture, but it's just to emphasize. Anti-Markovnikov. That's what we say when it doesn't follow Markovnikov's rule. Bromine on less substituted C. So just keep in mind that we're going to want to know why. It must mean we're not using the carbocation. The answer is usually in the mechanism, right? So, but unfortunately, we're just not ready for that mechanism. It's its own chapter in and of itself, the radical mechanism. So I'm going to say mechanism to be discussed. But if you have to have this at your disposal for future synthetic schemes where we put a lot of these together and we want options, you're allowed to use this because it is presented this early. Okay, but I actually cover it twice. I cover it here, then I do it again when we do the mechanism. So don't worry about the mechanism for this one yet. It will come, I promise. But you can be aware that everything doesn't go in Markovnikov fashion, and that's why I do bring it up here. It can be anti-Markovnikov. Okay, so just like we can do HOH, ROH, HX, we can do XX, two halogens. So, see what's over the arrow? Bromine, BrBr, aka Br2. Oftentimes the solvent's added. A favorite solvent is carbon tetrachloride, nice and toxic, but it is a good solvent, I have to admit. Gotta wear good PPE. So Br2 or Cl2 are the favorites for that. All right, let's observe that reaction. It's drawn out for you. Do we see stereoselectivity? In other words, look at what's going on with the dashes and wedges. They're very specific, right? If one is a wedge, the other must be dash. If the other one's a dash, it must be a wedge on the other one. They are never the same thing. They never match. They're never syn. They're never cis. They are always anti. That is not a regiochemical question. It's a stereochemical question. It's their relationship in space. They're on the same carbons. So that's why it's not a regiochemical question. This is a stereochemical question. They're anti. Their relationship in space is fixed. So you form two possible enantiomers. However, you only form the set of stereoisomers that are anti. You don't form the syn set. So let's write that down. The stereoselectivity of this reaction is anti-selective. BRs add, so in other words, BRs add. Don't worry, that space above is for the mechanism. But I wanted to make that observation because the product was given to us. The mechanism will show us how. Add anti to each other. So there must be something that's happening in the mechanism to explain why we end up with that anti configuration. What about regioselectivity? Regioselectivity would say, okay, we're adding a Br and a Br. Which carbons get the Br? But they each got one. So this is an irrelevant question. I'll write irrelevant here because both carbons, each carbon got one, right? We don't have to say which carbon got it since we added two things. We always do that across a pi bond. One atom has to fill its octet, so it loses the electrons, and the other one that took the electrons has to share it with something. They both were able to do that with a bromine. I think I'm spelling that wrong. There we go, event. So that part of your brain gets a break because you don't have to sit there and think which one gets it. They both, at least for now, both C's get a Br. So like I said above there, we will see this with Cl2, but not I2 or F2, okay? I2 mostly because we're going to form the I minus, and that's too stable to keep reacting. And I have that reason for F2 down here. F minus is too unstable. So the happy sweet spot is with bromine and chlorine. All right, let's finally get to the punchline, which is that mechanism. What is happening here? Okay, so we have our alkene. Here comes bromine. Bromine's not your usual acid that the alkene would really want to grab, right? It's pretty nonpolar. So what's going on there? Why would the pi bond ever attack the bromine? Concept of the induced dipole. That's what's going on here. When a bromine molecule approaches this electron-rich pi bond, it induces a temporary dipole. So the electron cloud gets distorted by repulsive forces to allow most of the electrons to build up opposing where the alkene is. Now that it's electron poor right there, the alkene is attracted to it. It can attack, but the bromine lone pair won't let that carbocation form. It comes back and attacks a carbon. So those two arrows, wait a minute, that means one bond to bromine formed here and bromine came back and formed a bond. Yes, we actually formed two bonds to bromine in this strange looking three-membered ring intermediate. Now, because the alkene is flat, this happens either above or below, but it has to be both bonds above or both bonds below because that three-membered ring couldn't do it any other way, right? Because look at what we're basically saying here is that the bromine, the bond to that one bromine, by the way, I forgot one more arrow. As it got attacked, this kicked off. Good leaving group, we're fine. So we have only one bromine left to worry about. But bromine is making two bonds, right? And so has a full octet, but it's positively charged. We have a bromonium ion intermediate. So just as that could have happened, this is planar, this could have happened to make both wedges come up to make a bond because it's not planar anymore. It's not sp2, it's sp3 now. So you have to consider dashes and wedges. So we could have had both wedges, or it could have come from below. We'd have both dashes. Right? We can't make a three-membered ring with one of each. They just wouldn't connect back. So we either made the ring like this, both up, or both down. But if one of the bonds to bromine was up here and one down here, we would never connect that to that three-membered ring. So that's why we have both dashes and both wedges. Now it's time for the nucleophile to attack. Who's the nucleophile? We just made it right here, that leaving group. So let's draw that in. This is a very strange intermediate, highly reactive, it has a name. It's called the bromonium ion intermediate. Bromonium. You want to know the names of the intermediates of the mechanisms because they're named, the names are they bother to have a name if it's important or kind of a key step. Bromonium ion intermediate. So we don't isolate this. It's an intermediate. It's not stable, particularly stable. It's very reactive because that's a strained ring and it's a positively charged bromine. It's ready to open back up. In doing so, it will give bromine those electrons it wants back. So what could we do here? We could attack, I'm going to do this color-coded, from the top. That carbon, if we attack that carbon, we can let bromine have its electrons back. That's better. Which means if this is the leaving group, now it only has one bond and it's to this one down here. But notice that if we attack, it has to be a backside attack because the wedge is already, that space is occupied and this is SN2 style. It's concerted. Attack, leaving group leaves at the same time. So it's got sort of SN2 character to it. So you can think of the new bromine coming in from the opposite orientation of the existing bromonium ion. So this is only going to attack this one from the dash position. This one's only going to attack from the top, or the wedge position, right? But it could have attacked either carbon. Could have attacked the top one. Actually, I'm going to do that one in red. Or the bottom one. Let's see which product that matches. Okay, so if it attacks the green path, if we attack the top carbon, that means the bottom stays a wedge. Bottom stayed a wedge. That means the top has the new bromine from a dash because it came the opposite of whatever the bromine ion was. So we have a dash wedge, dash wedge. So that's the green product. Let's make sure the red product matches. The red product says we take the bromide and attack from the bottom on the bottom, which means we attack the bottom C gets the dash bromine. Indeed it does. The top one stays the same in the red path. All right, now we have a bigger challenge. On the next one, bromonium ion that we could have formed, we clearly can only form the red or green scenario. So which one explains which? Well, in other words, when I draw in my arrows, I'm going to pick my color in advance. So I know that this can attack from the top, which means I have a wedge on top. That matches red, right? So let's pick red. 2 arrows for each path. Attack, kick off the leaving group. This better be green. Attack from the top, because it's the back of the dash, backside attack. So the bottom would have a wedge, and it does in the green path. So that's good. Okay, so there's 4 ways to get these 2 products from those different orientations the air intermediate could have had. You might say, wait a minute, if I just flipped over that intermediate, they'd be the same. In this one, they would be. So it's good to be aware of the unique ways they could always approach, right? Just because of symmetry, in this one they would be. But the reality is there's always really 4 possible ways for it to attack. But that got simplified to 2 things. So that's why we have the anti, right? They can't attack from the same side because there's like a little SN2 mechanism built in there, right? Has to do with backside attacks. That's how we got the anti. Okay, so another way some of these questions can present themselves is to do the opposite. Say, here's the product. What did the alkene look like? Okay, there's a little hint there with your intermediate, so you might want to pause, give these a try, and check your answers. Okay, so these were very similar. One key difference. One was the cis or E alkene, one was the Z alkene, same side, cis, or one was a trans alkene. What did you get? Here was a key intermediate, right? Can we see how we got that? Notice the cis framework here. So that means when we're done, so that's our key intermediate. So it means you have to be able to get there from your mechanism. But the bromonium ion really helps explain the mechanism. So you get there, then we say, okay, we have to attack, backside attack. Let's just draw one of them. Okay. Back, side, attack. Let's keep our cis framework the same to keep it easy on ourselves. That means this carbon over here stays a bromine wedge. This carbon on the right that got attacked gets the new bromine, but it has to be the opposite, backside attack. Hey, that doesn't look like any of our products. That's because they are not drawn with the syn framework. It has been rotated because that is the more stable way to draw them, right? So it's going to have that sort of zigzag framework. So that means we got to rotate. When you rotate something that's in the syn framework to something in the anti framework, it changes all things that are anti to syn and vice versa. So notice that I made these, when I rotated, I made the syn groups anti, but I made these anti groups syn, right? So if I keep this one fixed and I just rotate around this bond, I get that one. Pull that bromine out of the back toward me. You want to be able to visualize these things. Do we see how we get this one too? Key intermediate. Look at that framework stayed the same. The framework stayed the same, and they're anti. Is there an enantiomer? Normally, we draw both. So the relationship between these are that they're enantiomers. So I'm going to write that out. Racemic. Right? So this is a key intermediate, but don't forget we always formed this, also formed this one. And then you can get it to here. You can prove that it works out to that. All right? Fine, you don't believe me. Let's do one more step. So I open it up like that. And this keeps the dash bromine. This gets the wedge bromine. Notice how these match. So if I just rotate this, bond down, it equals that. So that's my racemic mixture of enantiomers. So racemic, you'll sometimes see plus minus. All right, so what about this one? The enantiomer is not drawn. Why not? Usually we form a racemic mixture. It just so happens that this one has a center of inversion, meso. So I could, if I tried to draw the enantiomer, I'd get the same thing. It'd be wrong to draw both when you're supposed to draw only one of the same structure, not lots of duplicates, right? So it just happens to be meso. Okay. All right. Now, how can we draw the product of this reaction? Well, without doing the whole mechanism, let's just go kind of fast. DMSO, by the way, is just a solvent. Carbon tetrachloride is a popular polar product, but so is DMSO, so don't forget about that. So key step would be to have that chloronium ion intermediate. So if we keep the framework the same, we'd have the anti options. Both anti options, right? These should be your initial products that you're thinking about. Now, you'll often look at your solutions manual and you will see the answer written like this instead. Are those the same? They're just conformationally rotated, right? So this is, see, wait a minute, I thought I formed an anti-relationship. Why are these syn? Because this framework has been rotated. It doesn't match the original one. So as drawn here, I'm not even highlight that right now. As drawn here, that is what the mechanism holds, and that's what your initial product drawing should look like. It is anti as drawn. But if you are, that is not to say there's a better way to rotate it when you're done. When all is said and done, if it can be out of that cis framework into the zigzag anti framework for the R groups that are large, then definitely that's going to happen. So when you rotate it, you see this became this one, and that one rotated to this one. Try that yourself with a model if you're still not sure. You got to be comfortable with that because it's just going to be assumed knowledge very soon. We won't always practice it every time. So get comfortable. Make sure that this makes sense, that these are the same thing. These are the same thing. Okay, don't go any further right now if they're not the same to you. Make sure you convince yourself they're the same. Okay, so there's a name for this product. It's good to have the vocabulary behind us because we will be saying, hey, go make this sort of thing. We make this alcohol. We made a dihalide. Not just any dihalide. A dihalide on adjacent carbons, also known as vicinal carbons, neighboring. Vicinal dihalide. So when you have a bromine or chlorine on neighboring carbons, you have vicinal dihalide. Okay. Now pause. This looks very innocent and benign, but it's not. What is going to make this challenging? We don't have a polar aprotic solvent. We have a protic solvent. We have water. We could also do something with other protic solvents or alcohol and get the effect we're going to see here. We're not going to make a vicinal dihalide. So first of all, the product's going to be different. It's going to have a different name. It's going to be called a halo. So there's one halogen. Hydrin. That's a hint that water did play a role. Water reacted, and alcohol would react too. In fact, let's take a look. This is your product. Notice how I drew those? And we're going to have stereochemistry to worry about too. So let's draw that in. What? Okay, so I told you this is going to be a challenge, but it's a very common reaction we'll be using. What you're going to need to do is possibly maybe open Spartan or build this alkene with your model set, your choice. Take out your model kit, build this alkene, or open Spartan and follow along with me, and then come back. See you in a bit with model kits or software. Open and ready to go.